So, welcome. This is ELE 210, circuit theory. Again, we've done Norton's theorem, and now we're going to take a shot at, we've done Thevenin's theorem, and now we're going to take a shot at Norton's theorem. And what we have is, I'm going to take the same circuit we had before and work through it. But let's talk about Norton's theorem. In Thevenin's theorem, we reduced any sourcing circuit to a voltage source and a series resistance. In Norton's theorem, looking back from the load, any sourcing circuit can be reduced to a current source in parallel with a resistance or impedance. Okay, and this, anything we do for a resistance, we can do for an impedance. Probably a lot more work, but it can be done. So the steps in this case, please note that the first three steps of this are exactly the same as for Thevenin's theorem. So we disconnect the load, we deaden all independent sources. And again, we'll talk about what a dependent source is as the course goes on. Voltage sources become 0 volts, which is just a short circuit. Current sources become 0 amps, which is just an open circuit. Looking back into the circuit from the load, which is disconnected, compute the resistance or impedance seen. This will be called R Norton or R sub n or Z sub n. And it will be exactly the same as RTH, our Thevenin resistance. So let's go down here a little bit and see what we're going to do here that differs is, with the load still disconnected, compute the short circuit load current, which is the current through a 0 ohm load resistor. In other words, we replace the load with a short circuit and compute the current through that short circuit. The resulting current is called I Norton or I sub n. And the resulting equivalent circuit, instead of being a voltage source in series with a resistance or impedance, it's a current source in parallel with a resistance or impedance. And here's our terminals, which will go out to our load. So let's go back to our example. This is the same example we had with Thevenin. We had some kind of generator, and that generator actually, had a Thevenin equivalent. It was a voltage source and a series resistance. And as I've stressed through electronics 1 and 2, voltage sources are really what drive the world electronically, electrically, whatever. And so that's why our generators, we model them, and they are essentially voltage sources. You can make current sources, but generally you start by using a voltage source to make one. It just seems to be the way it is. Mathematically, though, things are, there's a Thevenin theorem and a Norton theorem and all sorts of ways of handling that. So the mathematics doesn't care either way. Just in practice, it's easier to build a voltage source and then build something to give you a constant current. So we have our R1 is 150 ohms, R2 37.5 ohms, R3 150 ohms, and a 50 ohm load. So we previously solved this circuit using a total resistance method on page 2 of the Thevenin's theorem lecture, and we got 3 volts peak to peak at the load, and we got a load current of 60 milliamps peak. I said peak to peak, I meant to say peak. If I said peak to peak, I meant peak. Steps 1 through 3 are exactly the same as Thevenin's theorem. We said that. You can see page 3 of the Thevenin's lecture to pick up that stuff. But we found that our Thevenin, and therefore our Norton, because you're looking back into the circuit in the same way, deadening the same loads, you get the same answer. Our Norton is also equal to 50 ohms. So the only thing left for us to do now is to compute the short circuit current. And so we start with our circuit here. We start with our circuit And here's our here's our circuit and our 3 resistors, and then we short the load, and we're looking for the current in this short. So let's go with the total resistance method. What do we really have here as we look for the total resistance? We see our source, and it's in series with some glomp out here. Well, with this R3 shorted out, we could just replace it with a short, because R3 in parallel with a short equals a short, okay? And so what we really have is R1 and R2 are in parallel, because this point right here is directly connected to this point. So the total resistance here is equal to our source, that 50 ohms, plus R1 in parallel with R2. And R1 in parallel with R2, in case we want to give it a name, we can call this R12. So our total equals 50 ohms plus product over the sum of 150 times 37.5 over 150 plus 37.5. Turns out that this R12 is equal to 30 ohms. When you add it to the 50, you get 80 ohms. So now we have a total resistance of 80 ohms. The short circuit load current is equal to the current through IR2. In other words, the current flowing through here, all of it's going to go through the short, okay? Because this guy is completely shorted out. All the current through R2 is going through the short. So if we can find the current through R2, we've found the short circuit current. And in essence, it's the load that's short circuited, okay? So IR2 is going to be equal to VR2 over R2, and VR2, the voltage across R2, because these 2 resistors, R1 and R2, are in parallel, it'll be same as the voltage across that parallel combination, R12. And we can use the voltage divider rule here, because essentially we have a voltage divider. I mean, if we want to, we can draw a little circuit here. We can say there's our source. There's our source. And there's R12 right there. So we want this voltage of VR12, all right, and we can get that pretty easily from the voltage divider rule. The voltage divider rule says, well, first off, the voltage divider rule isn't the shortcut it claims to be all the time. It's just, you want the total current, it's VT over RT, okay? You multiply that total current, it's a series circuit, there is only one current, so you multiply that current by R12, R12 if you want to call it that, and you will get a current times, you'll get a current times the resistance, which is the voltage. So it looks like a shortcut, but it's not really. You can think of it as, we want R12's portion of the total resistance times the voltage. Or you can just say, well, VT over RT is the current anyway. When I multiply that current times R12, I'm going to get the voltage across R12. You do all that and you get 4.5 volts. So I come down here and I say, well, the short circuit current is going to be, it's this I2. So we have this voltage now is 4.5. So it's going to be 4.5 divided by R2, which is 37.5 ohms, and we get 0.12 amps peak, and this obviously is volts peak. Okay, probably should be a little more disciplined on that. And the result is 0.12 amps peak, or 120 milliamps peak. So now we have the short circuit current, which is going to be our Norton current, and we had our Norton resistance is 50 ohms. So we can build our Norton circuit up here. Sorry. There we go. So we can build our Norton circuit up here with a 120 milliampere I Norton and a 50 ohm R Norton, and our load is 50 ohms. Well, we can do a bunch of math, but it doesn't take a lot to see that, look, this voltage across these two, R Norton and R load, are the same. So half the current's going to flow here and half the current's going to flow here, and half of 120 milliamperes is 60 milliamperes, which is the answer we got in the Thevenin example. But if you want to do it for sure, you know, the voltage across the load equals the Norton current times the parallel combination of Rn and R load. Well, two 50 ohm resistors in parallel, the rule is whenever you have N resistors of the same value in parallel, you take that value and divide it by N. So that's, you know, 50 over N, and you get 125 milliamp peak times 25 ohms, you get 3 volts peak, and that's the same answer we got in the Norton example. So hopefully you can see how these equivalent circuits actually you know, are equivalent. They both the Thevenin equivalent and the Norton equivalent gave us the same answer as the total resistance method. And you might think, well, why do this? I can't remember if I said this in the Thevenin lecture or not, but if you had a circuit, let's go back to our original circuit here and try to get these things to lay flat. So if you look at our original circuit, supposing you wanted to evaluate this circuit for 20 ohms, 30 ohms, 50 ohms, 70 ohms, 100 ohms, you wanted to evaluate its, you know, what the output would be for all these different loads. Well, you could do the total resistance method on this whole circuit for as many times as you had different loads, or you could take the Thevenin equivalent and use the voltage divider method, or the Norton equivalent and kind of use a current divider method, if you will, and just get the answer more quickly and run off a bunch of answers. Now, you know, we have simulators and all that nowadays, but you know, and that's great, but one wants to be able to think about these things. The other reason these equivalents are important is that sometimes when we model various sources, we want to model them in the fashion of Norton or Thevenin. When we model the output of transistor circuits, we wind up with say a dependent current source and a shunt resistance or parallel resistance in a sort of a Norton equivalent, and you know, in power supplies, voltage source and series resistance, these are just really good tools to have in your toolbox and to know how to do. What we're going to do in the next video is we're going to solve a bridge problem with using Thevenin's theorem, and that problem like that was on your homework, and so I may be spilling the beans here, but we'll do a problem like that so you can see how the Thevenin's theorem approach makes that problem solvable, whereas it would not be solvable unless you knew how to do circuits with more than one loop in them. So until next time, many happy returns, and please stay tuned, and we'll have more information and homework and all that stuff for you. Okie doke. And there's a new lab in the lab folder, or in the Blackboard site. So please attack that lab, and again, we'll be talking about it. And if you want to have a office hours style Zoom meeting and talk about those labs, I'd be willing to do that. Best wishes, and take it easy. Bye bye.